So this is a test. I want to see if I can answer this in under 5 minutes or give a general gist of what the problem is in under 5 minutes. This one's validate binary search tree. And the idea is that all the left nodes need to be smaller than the value of this node, and then all the right nodes need to be larger than, right? So here, if you go left, you see a 1 that's valid. If you go right, you see a 3 that's valid. And here with the 5, if you go left, you see a 1 that's valid. If you go right, you see a 4, and that's invalid, right? Um, so I made an example here. 5, you go left, there's a 1. But if you go right, there's a 70. That way that one's valid, so it's not. So it actually acts as a better example. What are the bounds of all these, right? So what are the bounds of the node? Well, when you have a node, it's truly, it's unbounded, right? When you have a beginning node, anything can be a value for that node, right? So that's that value. What happens when you go left, right? When you go left, what are the bounds of this 1 here? Well, when you go left, because you saw this 5, the 5 becomes, right, if you were to split it here, the bound on the maximum. And there's no bound on the infinite still, right? So that's this bound. And if you went even further left here, it would be something similar, right? You would take 1 would be the bound. It would still be infinite, right? And if you were, so let's go to the other side. 5, you're going right, right? When you're going right for the 5, well, 5 becomes the minimum bound, right? You still keep infinity, right? And that's what is the conditions for the node going to the right, right? Here's the conditions. It's 5 to infinity, right? This is where it gets interesting. What happens when you go left from this point? Well, left from this point, from the 70 to the, I'm going to highlight it. From the 70 to the 3, that's left. Now, what have we seen on this side going left? Well, if you take a function node and you want to go left, well, we're updating the maximum, right? And for go right, we're updating the minimum. So let's say we're taking the 70, we want to go to the 3. Well, it's a new bound where we're updating the maximum, right? We're updating 70 here, but we're keeping the bound of the 5, right? So the condition that this node has to contend with is this right here, that it has to be in between 70 and 5, right? And going right, it's updating the minimum, right? 70 still going to infinity, right? And this is what the condition this 6 has to contend with. And at any point, if you get to one of these nodes and the condition is violated, well, then that's where you know that the bound is, the contract for the BST has been broken, right? So this is the major idea of this problem. And really the only skill that you need to solve this problem is to be able to traverse through the tree and keep these bounds valid, right? So you need a function that takes a node, takes a minimum bound, right? Or minimum value, you can call it, maximum value. And this is the core function that you have to write, right? And there's some like normal tree balancing stuff where like if the node is none, you just return none, or however you want to exit out of this function. And then going left means that the node dot left, which is being passed into this possibly recursive function, has an updated value, right, going left, which is updated in the max, right? So min value is unchanged. The max value is this node.value, right? And the recursive function going right is exactly what we wrote above, where you're setting a new minimum value. The max value is unchanged, right? And this is essentially the function in code of the core functionality of what you have to write. All right, thanks a lot.